is Advenit Makaya. I'm an advanced manufacturing engineer at the European Space Agency, and I have the pleasure of chairing this session on manufacturing. We have 6 very good speakers on interesting topics covering manufacturing and recycling. And we will start with Julien Granier from the University of Toulouse, who will tell us about the task force on ISRU that they have in Toulouse. Julien.
Thank you for the introduction. So really happy to be here. I'm a postdoc in the Institut Clément Ader laboratory in the Toulouse region. And so since it's the first time I'm presenting here, I will be developing and have a wide presentation on all our activities. So I won't go much into details, but if you have any question, feel free to ask them after. So yeah, I'm here to talk about a huge collaboration we have with other laboratories. So I'm a material scientist myself, but we also have some planetologists from IRAP, some biotechnicians from TBI, chemical engineers under the coordination of CNES, so French Space Agency. So our main activities are covering the production of a simulant and their characterization. But we use to do some direct additive manufacturing. So with the SLM laser melting process, we also do some indirect additive manufacturing that I will cover with the fused filament fabrication process. And so for which one we use some biopolymers, so that's why we need some experts in biotechnology. So starting from the beginning, we have our own simulant, which is called Basalt of Pic-Disson, which is placed in the center of France, in Massif Central. So it was actually one of my first PhD mission to get there and bring back some rocks, some basalt rocks. And so you start with those huge blocks. Why? Because we don't want them to be too much weathered. And then after a few crunching steps, we get some fine raw powder that you have here. And the thing is that we start at 100% crystalline material. So what we can do is actually melt the material at more than 1,400 degrees and then quench it to get some amorphous powder. So in a way, we try to mimic space weathering mechanisms and to see how maturity affects the processes. So as you can see, it's expected, but since we are using a basaltic rock, we have a chemical composition close to a marais region regolith. And so since we are quite low on titanium dioxide, if the aim is to see the effect of the titanium concentration, we can also add some ilmenite powder. So here you have the grain size distribution of our powder in the end. It's really nice for us because depending on the process we'll be using, we can separate this grain size distribution into some ranges. So below 20 microns, we use it for the fused filament fabrication process. And between 240 microns, we use that for selective laser melting for flowability reasons, mostly. Oops. So here you have the process. So we use a commercial SLM machine from SLM Solution. You've seen a lot of presentation about this, so I won't go into much details. So you have your powder layer exposed to a laser, you melt it, and then it solidifies. And so you have those nice glassy samples, like you can see here. So in our case, we use some vitreous silica substrate, and those samples here, they are cylinders we make for compressive strength tests, and we also use them, of course, to do some microstructure identification. So they are 3 millimeters wide, and as you can see on the cross-section here, they have some kind of homogeneous matrix, but they also have, of course, some defaults like porosities and cracks, but that doesn't have to be like an absolute thing. There's some things we can do to mitigate those effects and those defaults. Especially during my PhD, we found 2 important parameters. The first one being the amount of amorphous powder you have at the beginning in your mix So starting from a 100% crystalline powder here to a 100% amorphous one, you can see that we really increase the compressive strength of our samples. It's because you homogenize the sample and you lower the melting point. And then in a second time, if you take your samples at the end of the process and you anneal them at 900 degrees, so you have your glassy samples, and then you recrystallize them. And so you get this kind of microstructure, this network of diopsidic augite, which is quite more resistant, as you can see here, when you move from the white compositions to the yellow one. We really multiply the compressive strength of our samples. Oops. So, of course, there are some limitations with this process, since we are doing a lot of thermal gradients and the objects are brittle. And so there's multiple ways to mitigate that. We can do some modeling. For example, we have a paper going on with the characterization of thermal and optical properties of our simulants and EAC1. And the second aspect will be to add some reduced metals in order to bring some ductility and mitigate the effect of the cracks. The second process we use is a fused filament fabrication system. So you start with your simulant, you mix it with some polymer. So the simulant here, it's more than 60% of the volume. You make some filament with it. So we do that with a French company, which is 3D Ceram. They gave us as well a 3D printer adapted to the ceramic materials. So in the end, you have your object, the green bodies here. So they still have the binder in it. And then in the end, since we want ceramic objects, we debind them and sinter them to get those kind of things. The main aspect here is that all the gases that you generate during the debinding, we keep it for bacterial activity to generate again our polymer. So the good thing here is that we are in a closed loop system. So of course we need a lot of information to improve the process, going from the feedstock, especially the rheology, to adapt the printing strategy. We also some process monitoring, especially monitoring the printing temperature during the process. And then, of course, at the end, as we did for SLM, you can also do some microstructure identification and mechanical tests. So in the end, we have a PhD project going on to actually having some numerical modeling of this process. So one with a thermomechanical approach and one which is really considering the rheology of the fluid, and so which is really focused on the deposition step. So among all those things, we have also a lot of different activities, starting with some chemical engineering with the simulant reduction in molten salt. We also have some testing of fibers made by Fabercoat, and we analyze them with Allen University as well. We have projects going on feedstock optimization. And of course, we share a lot of our own simulant and data in order to do some collaboration between the different teams. So at this point, we are looking for several things. The first one being that, as we have seen during the conference, there's a lot of synergies between different laboratories. So if you can see some interesting aspect for you, feel free to come to me later. We also have an initiative to try to harmonize the trials we have in additive manufacturing at the European scale, because from one paper to another, it's quite complicated to compare the studies because you have so many parameters that change from one study to another. And then finally, we are looking for some applications because we have our technology maturing, but at this point, we don't have concrete applications for astronauts or in the context of lunar-based applications. So if you are industrials or space agencies with some ideas, please come to me later. So I think I'm a little bit ahead, but thank you for your attention. And so if you have questions, we'll have more time.
Thank you very much, Julien. Indeed, that leaves a few minutes for a number of questions. Do we have any in the room? So I can start. My first question is, you talked about improving the ductility of printed regolith by adding some reduced regolith, so some metals from regolith reduction. So people among us who have tried to work with reduced regolith know that it's actually a very complex and brittle metallic mixture. So do you think you can achieve improved ductility by this way?
We should compare the results from reduced regolith to ceramic one, let's say. But I don't see how the reduced regolith would be less ductile than the original regolith. And since we are starting so far away in terms of microstructural conditions, I think it can only increase the final properties. One idea we had, which is still under study, would be to maybe add some conditions in the additive manufacturing process to generate those reduced parts directly during the additive manufacturing step. So maybe that would make things better as well.
Okay. Do we have other questions in the room?
Timon Schild, Esric, thank you for the presentation. And I'm also talking as a representative of people that are struggling with reduced regolith. But I had a question more on the filler, so polymer regolith approach. What amount of filler can you go up to with this approach as a ratio to the binder? And then maybe secondly, you were talking about the recycling, so closing the loop on that. Could you tell us a bit more, maybe the efficiency, to what point you're able to close this loop? Thank you.
Okay, so for the first question, at some point, of course, if you are close to 100% of ceramic inside the filament, it's going to be too rigid. But we can go up to 70% in volume of basalt. But in mass, it's even further. But yeah. For the second question, we are not that far ahead because it's a PhD project going on the bacterial activity part. So we'll have some first results in the next few months, I guess. But it's a little bit too early to see how effective is the recycling part. So I hope that we'll be able to come back next year with some numbers.
We have time for one or two more questions, if there are any. I do have one more. You talked about standardizing the different manufacturing trials, which I think is a very good idea. What is your approach? Have you already constituted a network?
We are working on some paper with some Danish colleagues. I think we'll have to present those works in future conferences, but the idea is to find some common ground that would be easy for every laboratory who considers doing some additive manufacturing. So the main idea was centered on direct additive manufacturing at the beginning, but I think we can expand that. And so there's parameters that are really hard to modify in a laboratory and some which are quite simpler. So for example, choosing a common geometry of samples to generate would be one of the easy ideas, and having a common starting point simulant as well. So maybe getting help from experts on this domain, like the Vulcan facility, to decide which simulant could be a good basis for our common work.
Thank you very much, Julien. And our next speaker is Marvin Raupert from Leibniz University in Hanover, who will tell us about laser powder direct energy deposition in space conditions.
Okay, good afternoon from my side, and thank you, Advenit, for your introduction. So today I'll show you our progress in the laser powder directed energy deposition project under space conditions, and there especially the powder handling. And for those who are not familiar with our project, I would like to start with a small introduction. So why DED, directed energy deposition? It's a process where we could deposit the material on any surface we want and in any position. So in comparison to other additive manufacturing processes, we're able to not only to manufacture new components, so we could also code, join, modify, functionalize, and repair our components. And this is really important for the missions for Moon and Mars. And when we're talking about our material, then we have, in this case, in this process, two different options for our feedstock. The first one is powder-based, and the second one is wire-based, and both of them has its own advantages and disadvantages. What I want to highlight here is that when we are on the surface of the Moon or Mars, that we could use the regulus directly for our manufacturing in comparison to the wire-based. And in fact of that, we want to determine the influence of the environmental conditions of space to the process itself, so to the LPDED process, and the materials we are using in our research project. How we are doing that, here you can see our setup, which is developed for the drop tower facility, the Einstein elevator, and then we're manufacturing our specimens under microgravity, for example. Then we are doing manufacture some other specimens under laboratory conditions, under Earth gravity. The other manufacturing parameters keeps the same, and then we compare the specimens with each other to get the influence. This is the setup. The two levels which you can see here are a common interface in our drop tower facility. The diameter is in this case 1.7 meters, and the maximum height is 2 meters. This setup has a weight of 700 kilogram. We are using a diode laser with 2000 watt. Of course, because we are like a small satellite in a closed environment, so we have everything we need for our experiment has to fly with it. So the laser system has its own energy storage. We have 2 cooling circuits on board. We're manufacturing in the process chamber. And maybe the most complex part is still the powder conveying system, because it's really hard to keep the mass flow constant, independent of the gravity. For simulating the microgravity, as I said, we're using our the drop tower facility, which is called the Einstein elevator. This is part of the Leibniz University of Hanover, and it has 2 structures. One is for the guidance and one is for the drive system. And in fact, of the active drive system, which is a linear motor built over the whole length, we are able to accelerate our experimental setup for the first 5 meters with 5G, and then our experiment is in microgravity. So 2 seconds to the highest position, then it's falling again, 2 seconds, so all in all 4 seconds of microgravity. Our advantages are that we have a huge payload capacity, so up to 1,000 kilogram, which we could accelerate, and 1.7 meters in diameter, 2 meters in the height. And in an 8-hour shift, we are able to do up to 100 flights. So if you are interested in doing some experiments in Hanover in our facility, feel free to contact us. And here, last year in this Congress, I presented you the first results of the specimens manufactured in microgravity from August 2024. We showed that it is possible to use this manufacturing process under microgravity. We have seen no significant differences in the microstructure and density between Earth gravity and microgravity, but there was a higher hardness at 1G, which was possible linked to a smaller specimens volume compared to microgravity due to the increased powder flow in microgravity. So, and this is the topic. These are the 2 topics for my today's presentation. So what we have done in the last year is to optimize the powder feeder. now we can control our mass flow, and then we analyze the powder jet behavior downstream our nozzle. So if there's any influence in the powder focus distance, in fact of gravity, for example. Let me start with the first part. So here you can see the powder feeder system, which is here highlighted in yellow in the middle, and here you can see how it works. So the powder is in the powder container. The powder could rotate and move up, and then with the help of a scraper blade, the powder will be scraped into the center, goes then into the riser pipe, and one tube, the inlet filled with argon, the carrier gas, catches up the particles, and then we have a flow of a particle gas mixture. In the beginning, we thought that with the rotary speed and the movement in the upper direction, we could control our mass flow, but that didn't work. So in fact of that, we added a dynamic powder splitting system. The function you can see on the right side. After the powder feeder, so imagine we have now a powder mass flow of 5 grams per minute, but the deviation is really high. And what we are doing now is that we are reducing the mass flow to, for example, 4 grams per minute, but now we could keep it more constant. So there's a controller unit, which is a splitter system, 1 inlet, 2 outlets, and the angle of the splitter could decide which amount of powder is in channel A or channel B, for example. Then channel A goes through a cyclone. We are reducing the amount of particles, and after that we combining them with each other again with the Y connector system. So the volume gas flow of the carrier gas keeps constant. That is really important. Then we're measuring the mass flow with the help of the sensor system, and then these information are going back to the splitter. And here I just want to show you, this is a diagram with the mass flow, which was measured in the laboratory under Earth gravity, but we have also measured it in our drop tower facility. So now we are able to control the mass flow, and this is really important for us to do it independently of the gravity level. The second one is the analysis of the powder jet behavior downstream the nozzle, and there we wanted to see if the focus distance after the nozzle will keep constant if we change the carrier gas flow, the gravity level, or the ambient pressure level. Here just in fact of the 10 minutes, we have seen that the focus distance increases with an increasing gravity. In this case, the nozzle was in the same direction of the gravity. The video was done in our drop tower facility in microgravity. And when we increase the carrier gas flow, that reduces the focus distance. But the influence was so small that it keeps in the that it was still in the area of the manufacturing zone of the powder nozzle. So that is not a huge problem. But if we have a closer look to the ambient pressure, then we could see that this has a huge impact. So the powder focus distance has a shift in the direction of the gas expansions. Here we simulated this with a simple setting for a space station with normal pressure, microgravity, Mars conditions, and lunar conditions. Just don't worry, the 10 Pascal is there because that was the minimum limit in our simulation. And what you can see here is also that the velocity level of the gas flow, of the carrier gas and shielding gas, will be over 500 meters per second when we are manufacturing outside of the laboratory of habitat on the surface of the lunar and of Moon and Mars, and in fact of that, with the common process of LPDED, it would be not possible to manufacture the specimens because the high velocities would just blow away your melt pool. In fact of that, I'm also working on a new prototype system for feeding our particles and accelerating them to a surface, which could work without a carrier gas. So it's just pure mechanically the function. In 2 weeks, I'm then manufacturing new specimens in the Einstein elevator, this time with an enhanced powder mass flow. Again with the material we used before, titanium 6-4, but this time also with lunar and Martian regulus. Yes, and with this I would like to thank you.
Thank you. Thank you very much, Marvin. We have time for one question. Then maybe I have one, if you can disclose already, because it looks very interesting, this powder handling system without carrier gas. What's the working principle?
We tried to develop 2 different prototypes. The first one, imagine there is a centrifuge with an amount of valves, and at a specific point in the outer part, the valve will open, and particles come out. They will accelerate tangentially to your axis, and then you could bring the particles to your surface. The other one is with the vibrational concept. So with the specific frequency and amplitude, you could accelerate the particles. We worked on that. We made a parameter study. It works pretty good in the lab, but now we want to see how it works under vacuum conditions and under lunar gravity.
Thank you. We are looking forward to that. Handling powders in reduced gravity is always a challenge.
Maybe next year.
Hopefully. Thank you very much, Marvin. And we move to our next speaker, is Professor Alex Ellery from Carleton University, who will tell us a bit more about ISRO-derived aluminum characterization.
Slides. I'll just make the point that this is work done by my PhD student, Javier Walls. He's very secretive. He doesn't tell me what he's doing. So I'm having to present this with a limited amount of knowledge. But here we go. So our focus has always been, it's interesting that some of the talks today have mentioned some of the difficulties in reduced regolith mongrel metals and some of the properties that they have. We decided fairly early on to circumvent that problem. Rather than reducing regolith directly, we focused on basically anorthite as a mineral, as a source of metals. And it's a fact that about 42% of a spacecraft by mass is actually aluminium. In addition, the first generation of lunar bases are likely to be made of aluminium. So aluminium would be, if we can extract aluminium from lunar resources, it provides us with a mechanism for repairing lunar bases and spacecraft and so on. So these are the critical steps. We started off with LHS-1, lunar simulant, and what we produced was alumina. This is actually the core process. We produced alumina, and then we reduced that into metal, and then drew that into wire feedstock, and then used electron beam additive manufacturing to produce structures. So we started off with the LHS-1, and the first thing we did was to separate out the iron component using magnets. Very, very simple, nothing terribly dramatic or sophisticated. And down here you see, is this the laser pointer? Yes, okay. Down here you see, this is the solution after we performed HCl leaching, which I'll talk about in a moment. This is actually without beneficiation, and this is with beneficiation. As you can see, the iron makes the fluid very, very murky. So this actually shows that we didn't do any reduction on the unbeneficiated one because we didn't really have the facilities and the time to do so. So we focused actually on the beneficiated version. So this is the leaching process, HCl leaching. As you can see here, we use HCl. This is the anorthite here. And what we're doing, that you also add water, what we're doing is we're generating aluminium chloride. Deposited out of this, directly out of solution, is silica, which we then extracted and then dried. And in solution, there's calcium chloride. We didn't actually extract this, we kept it in solution. We could have actually extracted it and put it into the next process, but we didn't do that. We were focused primarily on the aluminium. But what we've done, effectively, we've shown that we can actually take the anorthite mineral and extract 100% out of it. It's 100% useful material. So the next stage was to roast everything, calcination. And we dried the silica. We then discarded it because we didn't use it for anything. We could have turned it into glass or something like that, but we didn't actually do that. Again, so we calcined it and ended up with alumina here. And in fact, we also recycled the majority of the hydrochloric acid that we used. So this is the third stage. This is the molten salt reactor, or FFC process. This shows you the internal configuration here. This is the external configuration. We built this in-house and basically reduced the alumina in a calcium chloride salt, molten calcium chloride salt to generate aluminium. Now, we went through a couple of different processes. This was the first attempt. It didn't look very nice. This is with another attempt. This is actually some of the aluminium we ended up with. And then finally, this is what we actually ended up producing from the liquid. The liquid is tapped off because it's molten at 900 degrees, aluminium. And we managed to produce these kind of like aluminium pellets. So the next stage of the process was to try and use it as a construction material. This is actually, we cast the molten aluminium in these casts here. We then actually processed it and cleaned it up a little bit, and then we rolled it very laboriously to thin it out a little bit, and finally drew it into wire, which you see spooled here. The next stage was to take that wire, put it into an electron beam additive manufacturing facility, shown here. We played around with the voltage, current, and so on, and various other parameters like the speed and so on, and ended up with a wire here. This is actually a test. This is actually a test line, which we'll see built up in the next few slides. That's just the first line being laid onto an aluminium build plate. So this is the first result. We call it the turd because it doesn't look very pretty. But this is what we use for slicing. We slice through this to get a cross section of it. And here is actually the same metal actually being used to build a kind of plate, and I'll show you that in a minute. This is the microstructure. So here, when we took a section through that turd, this is the upper part. So this is the actual what we deposited in layers, and this is actually a section through the build plate. And as you can see that there was good bonding between the two. This is a micrograph. This is like a microstructural picture. And as you can see, the amount of porosity in the actual laid aluminium is actually very, very small. It's very, very limited. And this is actually a blown-up version. So each of these pores is only about a micron across. And there weren't very many of them. So Javier carried on doing some testing. He did explain this to me, but I don't think I was listening. Apparently, if you compare the off-the-shelf aluminium 1100 series with what we deposited, you'll see that actually the yield strength of our deposit is higher than the commercial off-the-shelf. All the other parameters were almost identical. So we're getting very good results in terms of the mechanical properties. And this is the bit we're most proud of. We decided what we wanted to do. We didn't like the look of the turd very much. So we thought, well, let's build a little fuel tank, a minuscule fuel tank. So this shows you the process. We did it in 2 halves, and then we polished it and basically milled it into a proper shape. And this is, you can see this is actually the final result, and you can see that it's hollow here. And then when we did that twice, and then we basically used the same machine, the same EBAM machine, to weld the 2 pieces together. So this is the team as it stands. Javier is the one who's not here. He's the one who did most of the work. Bertrand did most of the HCl leaching phase. Kate is a professor of chemistry who we work with, because I'm a roboticist, I don't know anything about chemistry. And Priti Wanjara is at NRC. We've been partnering up with her. And this is all the NRC team, and there's me. Okay, I'll leave it at that. Thank you very much.
Thank you very much, Alex. We have plenty of time for questions.
Thank you, Alex. Amazing presentation as always. We get to hear a lot about the exciting work that you do, and it's a pity that Javier could not be here, and you did a great job of covering for him.
Thank you.
So let me see if you can maybe answer this. Are you able to share some specifics on the power deposition which was done with regards to the aluminum, so we can kind of understand how it was done? And are you able to attribute the lack in porosity primarily to the high vacuum within the electron beam manufacturing process itself?
That's a very good question to which I do not know the answer, but I can put you in touch with Javier, who I'm sure can answer you. Yeah.
Thank you.
Robert, we have
Thanks, Alex, for the nice talk. Aluminium 1100 is nice. 5, 6, or 7,000 series would be nicer. Have you thought about that?
Yes.
How to get there using your process?
Yes, I have actually. 6061. I think we can replicate on the moon, apart from there's one element in there which we can't substitute for. It's actually a very minor constituent. Is it zinc or something like that? Zinc, yeah. Yeah. At the end of the day, we think that if you eliminate the zinc, it will only have a minor effect on the final performance of the metal. So yes, in theory, we could produce 6061 from lunar resources, or a version of it.
Very nice.
Okay,
Thank you.
Do we have other question? I have one, but I'm waiting to see if... Yes, Timon.
Hi, Timon again. Thanks for the presentation. I just was wondering, because earlier today, you were mentioning that you didn't connect the aluminium production part from electrolysis with the actual printing. Is that so, or did you actually connect those two processes?
Let me reiterate that. So yes, there is an overlap. So we used an off-the-shelf aluminium alloy for printing, but we also used an off-the-shelf alumina, which we then reduced, and then we printed. So we did have an overlap, but we didn't have a complete all the way through to the HCl leach. That was the break point.
Okay. Thanks for the clarification.
Yeah, that was actually my question. So you used off-the-shelf alumina.
Yeah.
But if you had to produce the same amount of aluminum, how much initial regolith would you have to put in the system?
Well, what we found was that when we did try to do the entire cycle, we couldn't draw the wire from the HCl leach process because it was just too brittle. I think this emphasises that the importance of effective beneficiation. If we're going to do this in real life, we're going to have to beneficiate much more strongly if we're going to pull all the way through to the final, to get a viable final product. I don't know the answer to the action in terms of numbers and proportions. So.
Okay, understood. We have time for one more question, if there's any. Okay, then we just thank Alex. Thank you very much.
Thank you.
And our next speaker is Lanie McKinney from MIT for the first of the 3 talks on using debris and waste as a resource. So Lanie will tell us about injection molded composites from mission waste.
Awesome, thank you so much. Hi everyone. Yeah, excited to kick off the section on recycling and also manufacturing as well. So happy to be here. The subject of my talk is recycling astronaut trash and a perspective of that astronaut trash as space resources. So this is a picture of NASA astronaut Trunal Patil aboard the ISS, and he's surrounded by cargo transfer bags filled with trash. This trash is what we call logistics waste. It's all of the items that are sent up, storing food, water, pharmaceuticals, everything that enables the launch of those materials and keeps the astronauts alive. And it's actually quite a substantive mass flow. So when we start thinking about sending humans to the moon and spending more time there, we're actually going to start to accumulate a lot of this trash. So if we send a crew of 4 for 1 month, like some of the Artemis missions have planned, that's almost equivalent to a full iSpace Ultra CLIPS lander, about 3/4. If we do a crew of 4 for 6 months, it scales to about 5 of these landers. And if we send a crew of 4 for a year, we're actually we're making about 2.5 metric tons of logistic waste that will end up on the surface of the moon. And this is almost a full Blue Origin Mark 1 lander. So as we spend more time, more crew months on the surface of the moon, we're going to accumulate a lot of trash. So this is a Space Resources Conference, so I want to pause and connect to what's going on kind of in the broader space resources ecosystem. So typically when we think of space resources, we're thinking the regolith and the water ice and what materials are present in these items. But we could also broaden our definition of space resources to include mission-derived waste. This can include plastics and polymers, metal scrap, insulation, textiles and soft goods, many items which will reach the end of their useful life and then will just accumulate on the moon. We've spent the energy to get these items there, and they have embedded manufacturing value and utility. And so if we can find ways to reuse them and recycle them, we actually are using this new space resource that we've actually created. When we do this, we can achieve similar aims to ISRU. Aims like reducing resupply needs if we can make functional parts. We might even find energy efficient ways to manufacture items instead of having to process regolith as much. We can kind of subsidize some of these parts with more efficient manufacturing processes. And generally, we can avoid polluting the moon and the accumulation of trash in lunar landfills. So how do we recycle logistics waste on the moon? So there's 3 buckets, 3 kinds of materials for the most part that make up logistics waste. This includes pure metals, thermoplastics, and then this other category. So basically anything that's not does not neatly fit into those first 2 categories. And so these are the buckets. And we know how to recycle pure metals. For the most part, we can melt and recast these materials. Same with thermoplastics. We can melt and reform them. But what to do about this other category? This other category can include things like nitrile gloves, foam, drink pouches from food systems. And in fact, we're interested in ways that we can recycle many of these kinds of items at once, because we cannot necessarily have, when we start out, a dedicated recycling process for each individual kind of logistics waste. So one solution to this is to actually combine these two, to treat the thermoplastics, or to use the thermoplastics as a matrix material in a novel composite, and then use these other categories as filler material. So instead of thermally recycling, we're mechanically recycling them. So this is the core concept of a recycling and manufacturing architecture called Cerberus, and it is an acronym. It stands for Composites for Extraterrestrial Recycling by Engineering the Reuse and Upcycling of Zootech. And this is an MIT team submission to NASA's Lunar Recycle Challenge. So our concept starts with the thermoplastic and filler materials that are present in logistics waste. We cryo-grind them, embrittle them, and then grind and sieve. Then we take these grinded materials, we put them in an injection molding machine, and then we can make functional parts as long as we have the molds for those parts. Then with pure metals, we can do something similar. We can cast the metals in a mold-based process, and then produce structural materials, things that we couldn't otherwise make out of plastic composites. And this is the concept. Also, the idea with the molds is you can manufacture these, hopefully. There's some synergy with construction technologies using regolith, and we can actually potentially make these molds out of regolith, supporting the sustainability of the architecture. So this was our concept that we submitted to the Lunar Recycle Challenge. The concept we developed as part of phase 1, and then we were awarded some money to develop a prototype system. And today I'm going to kind of report on that prototyping progress, and specifically related to some of the novelty in the injection molded composites process. So for the first step of the process, going from the materials to these grinded up parts, we use liquid nitrogen to embrittle the materials. Ideally, in the lunar environment, we're going to leverage the vacuum and the cold temperatures on the moon actually to embrittle these materials, but for the Earth-based process, we need some mechanism of embrittlement, and then we grind and sieve these materials. So we've done this with nearly all of the materials that are present in the Lunar Recycle Challenge, but here's a couple examples of the kinds of what these ground materials look like. Polyethylene bags, this is the nitrile gloves, Zootech F30 foam, and then these are the plastic metal pouches. Then going to the next step, going from our ground materials to injection molding, I'll kind of walk through the process a little bit. We take those materials, mix them up, and then we load them into the barrel. We melt the material around 200 C, but we have the ability to change that temperature. We inject into the mold, and importantly, this is actually a commercial benchtop system that utilizes a spring plunger system to apply that pressure and move it forward. And then we are currently creating dog bones to characterize these novel composites. So that's a picture of 10% Zootech and polyethylene dog bone. And then we also are doing tensile and a range of material characterization tests. Another track in this competition is actually developing a digital twin of the prototype. So I wanted to briefly touch on this as well. It's a separate track and separate effort almost, but it has a lot of value for space systems and improving the prototyping process. So we have a general prediction model that's made up of a few different components. The first is real-time system data from our machine. We also have a dynamic system model that goes into this prediction model. We have physics-based models specifically predicting the fill, warpage, and shrinkage inside the mold. And we're working on developing the different geometries of our parts. Right now, we're in progress making the dog bone. And then we also have a machine learning model that we're developing for predicting tensile, yield strength, and hardness, which might be difficult using other models. And the advantage of this is that we can get some predictive capability for process optimization, and then in the future, the system can have real-time autonomy and control for managing risk. So the takeaways from Cerberus so far, this is an ongoing effort for the Lunar Recycle Challenge, but so far we've performed a proof of concept demonstration of recycling these composites in this way, and we've also achieved very energy efficient performance. So it's about 1 kilowatt hour per kilogram of product that we're able to make. Varies based on the material and the fill fraction, but around 1 kilowatt hour per kilogram. Our future work, especially for the last phase of the challenge, is to test other materials and fill fractions, specifically higher fill fractions, to use more of these filler materials. We want to manufacture our representative products, so we're in progress making the molds now. And we want to leverage the full power of our digital twin that we're developing. So briefly, I just want to give acknowledgements to the entire Cerberus team. It's a great source of pride that this is actually a student-led team that's submitted to this NASA Centennial Challenge. And then also a big thank you to the co-leads that are present today and our advisor. Thank you. I'm happy to take questions.
Thank you very much, Lanie. Any question? Yes, we have a question in the room. I don't know who was first, but let's start with Alex.
Hi, thank you. Is there any reason why you picked molds and casts instead of 3D printing and additive manufacturing?
Yes, actually, there were a couple reasons. So I didn't even get into the piece of the architecture where we're actually planning to extrude filament from our injection molding system, because we recognize the inherent value of 3D printing processes, which are flexible for space environments. But there is also a need for standardized parts and standardized products, especially if we're trying to make life support system components and things that should be standardized and potentially have a high throughput. And so we wanted to focus on a kind of manufacturing technology that has been historically not as explored for space applications. But 3D printing, again, is a complementary and a very valuable technology for, I think, another set of applications. We are interested in making standardized parts.
Thank you. We had one from Omi, one from Aaron. Aaron?
Yes, thank you for the talk. So did you look into also how many times you can recycle, grind, and injection mold these parts? If you go to a polymer conference, this is usually a huge topic, especially for, let's say simple polymers. They usually say 4 or 5 times because of the shear and the mechanical forces and sometimes the temperature, but I see that you use cryo systems, so maybe that's not that much, but yeah. Did you look into this?
Yes, so this is a piece of our study we have not gotten to yet. We're very interested in the question, how many times can we recycle this? Ideally several times. The good news is we're not trying to achieve any major structural properties of these materials. We're trying, it depends on the kind of product that we're making, but ideally we could make things with less stringent mechanical properties and requirements, so we could recycle it multiple times, but it's a piece of the study we haven't gotten to yet. So I'm also quite interested in that question, and your point well taken.
Okay, thank you.
Omid. We had Omid first. Yeah.
Lanie, I appreciate your effort to make Moon waste-free. It means a lot. But my concern is, have you calculated how much mass you need to bring there to recycle 1 ton after 1 year stay of the people? Thank you.
Sorry, can you repeat the question one more time?
Yeah. Did you calculate how much mass you need to bring there as a recycling process and production for different mass? How much it's weight? Thank you.
Yes, so this is, we are testing a prototype system. This isn't like a full architecture that's planning to fly, but we did choose a modified commercial benchtop injection molding system. So it's about, the mass of this system that we're using is about, I would want to say 30 or 40 kilograms, maybe 50. So our system is actually quite small compared to large industrial injection molding machines. And I think if it were to be pursued on the moon, you would design and optimize a system, specifically for those environmental constraints. But generally speaking, we're able to achieve this in a relatively small system. And the idea that we could, the mass savings from the recycling process far outweighs the infrastructure required to maintain this process on the moon.
Sujit.
Thank you, Lanie. Amazing presentation. Sujit from Public Access. What are the health impacts to the astronauts if this process is performed within the habitat environment? And what are the challenges if it is performed outside in vacuum?
That's a great question. So we address this a bit in the environmental section of our phase 1 study. The idea is that this manufacturing process does create things that you would probably not want to manage in a controlled life support system. So the best place for this kind of manufacturing, for safety, for risk, is probably outside the habitat. So there's actually things that are advantages about operating in the lunar environment. The challenges, which I will address, are definitely the temperature swings, which we're hoping that we'll have great solutions for keeping hardware warm and functional and operational during the lunar night, and also technologies that can effectively mitigate dust so that it's not eroding mechanical parts in our system. So ideally that will need to be thought about in much more detail. But generally speaking, the idea would be for it to be outside the habitat to avoid some of those health impacts and to risk and to the life support system. And I think there will be technological solutions to help manage it outside the habitat.
Thank you. Then you have one more, and then Robert. Yes, then Robert.
Yay, it's my turn. Thanks, Lanie. Interesting talk. I have two questions. One is, we have not discussed any kind of, say, biogenic waste at all. So packaging or, food waste, maybe human waste, stuff like that. Have you even considered that, or you really focus on these materials? Okay.
We're very focused on logistics waste.
Right.
It's the scope of the Lunar Recycle Challenge to be the packaging, and we even proposed like a cleaning process for consumable or packages that had food particles on them, but they actually de-scoped, and they wanted us to focus on the recycling system and not so much the biogenic stuff.
Okay.
So outside of the scope.
Yeah, got it. Then one question I would have is maybe a lot of the challenges can be overcome by a priori selecting the materials you use, so you have a better control over it. Is that, considered in terms of what is the backward impact on the engineering eventually?
I think your point is well made, and it's actually something that we discussed in the initial phase of the project, that if we were to select materials from the beginning that are more easily recyclable, then this kind of potentially circumvents some of the issues that we're facing. And then I would say that the caveat to that is it may take a long time to turn around the current trajectory of our materials characterization and aerospace grade rating. That's Zootech foam, for example. We just don't have a lot that's mass efficient like it, and I think it's very unlikely that they will find a good alternative in the near future. And so it's a primary focus of the competition. So I would agree with you and say that potentially there's an intermediate solution that this perhaps will also be needed in addition to selecting different materials in the mission manifest from the beginning.
Great, and that leads to the last bonus question is, the composition of the different materials. Ideally, you would essentially take a DML or something like this, and you know exactly what are the materials, what is the percentage of the materials, and you make your little cocktail out of them. Why I'm asking that is because there are a couple of materials which are not brittle at minus 100-something degrees eventually. hardy stuff like Teflon, for instance, PTFE. Okay, there's a phase transition to minus 115, but still, they are still moldable and not brittle at all. So have you considered that?
Can you repeat, summarize the question just a little bit?
What I was thinking is like the representativity of your material mix is based on what? I mean, if you have a spacecraft, you have a declared materials list, for instance. You know exactly the amount, the batch, whatever, exactly what it is. So you can essentially make a cocktail out of that.
Yes. So if I'm correctly understanding your question, it's about the specific waste items chosen. Those are specified in the scope of the Lunar Recycle Challenge. So there were 17 waste items in phase 1, and there's now 8 in phase 2, and they were selected based on the current representative mission manifest to the ISS. That's where they come from.
Thank you.
Yeah. Then the very last question. Otherwise, we are running late. Yeah.
Very interesting. Just a quick comment that we're working with the logistics reduction team at Johnson Space Center, and you probably know that they had a one-time opportunity to catalog everything from Artemis 2, and so there'll be much better data coming out on what's available because prior a lot of it was deorbited. So stay tuned.
Oh, thank you so much.
Thank you very much, Lanie. Thank you for your questions. Our next speaker is Trunal Patil, a local researcher from Ellery, who will tell us about the lunar hardware recycling system for space waste.
Good evening, everyone. Welcome and thank you for staying almost end of the day. Myself, Trunal, and I'll be talking about development of the lunar hardware recycling systems. So let's imagine we are standing on the lunar surface from 40 years now, I hope. Mining systems are functioning. Rovers are operating on the moon surface. But what will happen if there is a breakage on the lunar hardware? Lanie already discussed about logistic recycling. But what we're going to do once end of life of this lunar hardware? So today, here I'm presenting about from this end-of-life hardware to usable resources through the development of the lunar hardware recycling systems. So even without permanent lunar residence, there are total 77 numbers of objects have landed or crashed or intentionally impacted on the moon surface. Which is around 227 tons of hardware currently on the moon surface. And this amount is expected to rise as private and government organizations intensify their focus. And in the upcoming ISRU activities, we need more hardware. And transferring this hardware from Earth to moon is like expensive, and in this case, recycling is a low-hanging fruit, which will be very useful to create valuable resources. So what we are proposing here is like recovering usable materials from this lunar hardware, and basically how we're going to do is like we wanted to use mechanical physical recycling methods. Basically using the size reductions and physical separation methods. So this is a dry mechanical physical recycling methods using the centrifugal methods to liberate the particles. And after the liberation of the particles, we want to separate using the electrostatic separations. And we tested with these metals with the space-grade aluminums, space-grade cables, and printed circuit boards. So why we wanted to do liberations? Because liberation is an essential parameters, because these metals are stick together. If we don't liberate these metals, there will not be separations. And if we are not going to separate these metals, it will limit the reuse applications. And that's why we need effective size reduction process that can handle the heterogeneous materials. And also, we wanted to use the centrifugal force to compensate for the lunar gravity. So basically, using the fully dry recycling process to overcome the lunar constraints, because on the moon we don't have the we don't know how much water we do have, we don't have the chemicals, and we do have limited infrastructure. So we wanted to use simple mechanical dry recycling systems that can give us highly pure materials with this from this lunar hardware with the minimal moving parts. So we use this centrifugal mills. Basically, material is fed from the tops, and due to the impact and shearing between the rotors and stationary sheaves, the material get reduced into size and pass through this sieve, and the bigger particle stays inside for the further grindings, and basically the size reduction happens in these principles. So basically, we tested most commonly found materials, basically space-grade aluminum alloys, aluminum 2024, aluminum 6061, and aluminum 7075. And then we also tested space-grade cables, which is combination of polyimide and silver-plated copper and printed circuit boards. So interestingly, even though it's aluminum alloys, we found very interesting result in the aluminums. What we found is like aluminum 2024 and aluminum 7075 processed successfully. But in the case of aluminum 6061, we found jamming issues. And as you can see in the pictures, basically, these aluminum 2024 and aluminum 7075 particles are a bit smaller compared to the 6061. And you can see in the this particle size distribution as well. So basically, we wanted to see like how this, why this is happening in the aluminum particles. So we further examined this effect with the composition analysis, and we did a composition analysis. And what we found is like there is a composition variation in this aluminum space grade alloys. So in case of the aluminum 2024, which is rich in copper, so because of that, this material is less ductile compared to the aluminum 6061. And in the case of aluminum 6061, which has the balanced composition with the magnesium and silicons, so that's why it has like good ductile. So aluminum 6061 in this size reduction process, instead of fragmentations, it get deforms. And in the case of aluminum 7075, it has a high zinc and magnesium contents, and basically because of that, it's less ductile, and that's why aluminum 7075 gets easily fragmented during this process. And also with the material properties, what we found is like aluminum 6061 has relatively higher elongation value, and that's why the aluminum 6061 shown less jamming issues. So what we found is like during the size reduction process, this process performances depend on the material properties, and we had to this performance varies with respect to each lunar hardware compositions. So in the next, actually, we also verified the energy consumptions. So basically, we tested this all three different feedstocks, aluminum alloys and space-grade cables, PCBs, on different RPM speed. And basically, what we found is like when we increase the RPMs, the energy consumption is rise, and then aluminum alloys required highest energy. And then also we measured the temperature inside the chambers, because we wanted to see like how the temperature varies in this size reduction process. And what we found is like when we increase the rotor speed, the temperature rise. And notably, there is a higher temperature rise for the metal aluminum alloys kind of materials. So what it says like this process for performance is depend on the material types. What are the materials we're going to shred it? In the next steps, once we do the size reduction process, we also wanted to separate these materials. So basically, what we use is like the turbocharging free-fall electrostatic separators with the collaboration with the Imperial College London. So what we done is like the material is fitted from the top turbocharging device. And based on the properties, either particle gets positive or negative charge. And then positively charged particles, when free falls to these two different plate electrodes, the positively charged particle get attracted to the negative plate electrodes, and negatively charged particles get attracted to the positive plate electrodes. And that's why there is a separation happens. So we use these electrostatic separations for the separation of the metal to non-metal particles. So here you can see this is the mixture from the space-grade cables, and you can clearly see there is a good separation between the silver-plated copper and polyimide, because this is a space-grade cable which made of silver-plated copper as a conductor and the polyimide as an insulator. And you can see that there is a clear good separation achieved using this turbocharging free-fall electrostatic separators. We will further analyze these investigations, the performance of the electrostatic separations with varying the electrode voltage. In the separation process, there are so many different parameters, but we wanted to see like how the performance varies with varying the electrode voltage by varying the 5 kilovoltage to 30 kilovoltage. And what we've seen is like the larger particle shows highest purity. So what it says, like the particle size is also really critical for this kind of separations. The second thing is like what we achieved is like the purity of the polyimide with these electrostatic separations from to impressively high, from 12% to 82%, which is quite good. And in terms of spacing distance, we varied spacing distance from 0.15 meter to 0.30 meter. And what we found is like smaller spacing distance gives highest purity. So with that, actually, I wanted to conclude some of these results. We tested mechanical physical recycling methods. Basically, what it says, like using the lowest optimal RPM, it gives reduced energy consumptions, and centrifugal milling is effectively liberates the materials, but the performance is strongly depend on the material types. In terms of turbocharging free-fall electrostatic separations, it's highly effective for the metal to non-metal separations, and purity can be increased from 12 to 82%. But the important factor is the particle size is critical. Then the key takeaway is like the mechanical physical recycling depends on the materials, particle size. But this is a very dry and reagent-free recycling process, which is very highly ideal for the lunar applications. So with that, thank you for your attention, and I'm open for your questions. Thank you.
Thank you very much, Trunal. We have time for a couple of questions. Yes, Sujit.
Great presentation. Have you considered using, for metals specifically, friction stir mechanisms where you can probably use the feedstock? If you're putting in so much energy into centrifugal separation processes for metallic compounds, if you're using friction stir, you can actually use that same process, that same amount of energy, and kind of extrude the metal into a feedstock, which may probably not be what you want for this particular project, but have you considered something along these lines?
Thank you so much. That's really interesting questions. Actually, when I was doing literature, actually, I came out these friction stir methods. In this project, actually, I specifically look for the mechanical physical recycling methods and the grinding only. But I think in the near future, maybe we can explore that point. But right now, I haven't explored that particularly. Thank you.
Thank you. Any more questions? Yes, I have a question then about the aluminum alloys. Since it's the 6061 is jamming because of the higher ductility, do you have ideas on how to mitigate that? We saw an example with the presentation from MIT about using cryo treatment to increase the brittleness. Do you have other ideas?
Yeah, I think as pointed out by the Lanie, actually the cryogenic here, the cooling might help in this for the aluminum 6061 because the aluminum 6161 is more ductile. And this is the one of the way actually can help. But right now, the grinding actually I'm using, there's no heating, heat transfer way. So I haven't really tried with that way. Yeah, but that's the all actually I tried for this specific aluminum 6061 alloys material. Yeah.
Thank you very much, Trunal. And we move to the last talk from this session. It's Stella Tkatchova. I saw her in the corridor. I don't know if she... yes, Stella is here. From ESMEA, who will expand even further the scope of space resources by including space debris. So the floor is yours.
It's actually, we wrote together the abstract.
Okay, so Stella and her colleague, I'll let you introduce yourselves.
So this idea came out a few months ago. And the idea was about treating space debris as a resource. And you know, I'm quite passionate about it. So it's a valuable in-space resource. And we need to learn how to use it and reuse it. And now I'll just give a very quick overview of the problem which I see, and then I'll transfer it to Jeff. So this is data we had in 2023 from the ESA updated space environment report. Exactly almost 3 years later, you see the new data. So you understand very clearly the situation is quite serious with the space debris, particularly critical, the small parts. And we have 15,800 tons. So how does that compare to the weight of any space assets? As you can see, the current ISS is 420 tons, I believe. Modern LEO constellation. So it's a huge amount of hardware we have. So it's very scary when you see that data. But you know, all of you, that current satellites are not built to be serviced or recycled in any way. And this is a huge issue. But the other issue is, when we look at the various active debris removal concepts, they're very diverse, they're very complex. You have net, harpoons, grippers, magnets, tethers, all at different TRL levels and a different type of maturity. But there is very few ideas for small debris. How do we actually remove, capture, how do we capture and remove the small debris, which turns to be lethal, actually, and very difficult to track, and having a lot of negative impact on subsystems. But we know that space debris contains very valuable material. So imagine if in the future, it's easy to collect space debris in the long-term future, from 1 to 10 centimeters, and it's easy to recycle it. So we jump away the step of the recycling, just thinking directly, what do we do with the collected space debris? So with Jeff, we were discussing, and an idea which came to my mind was the first step is we do a feasibility study. Is it valuable actually to recycle this debris? Is it worth it, or are we just wasting time and resources? What are the trade-offs? What is the TRL? How do we describe the debris which is there? So what type of technologies we use? How do we detect, describe it, see from what's made the debris? We do RPO. We do have already the technologies both for space-based SSA and both for RPOs. We can use the ones for iOS. We have for collection of space debris, active debris removal, different concepts. But in the e-space logistics ones is the one missing. So there are some trade-off scenarios which we looked at, because recycling and reuse debris will support future in-space assembly, manufacturing, and in-situ resource utilization. So here are the scenarios. One big hypothesis is, and it's a very wild hypothesis, but long-term one, there will be space debris collectors and recyclers for space debris. So this is a hypothesis, so don't shoot me for that. And the three scenarios. The first scenario is that the collected space debris, we dock it to a low Earth space station, actually. And then it's used for metal powders, for aluminum, titanium, or for metal 3D printing. There, the benefit is in-orbit processing, immediate reuse, no launch costs, but of course limited capacity, extra workload for astronauts. Scenario B, return to Earth. Quick recovery, mature industrial scale-up, but there is re-entry cost. And the third one is combined. You actually dock to the space station, the astronaut supports the sorting, or in that uses the sorting, and then parts which are more valuable or there is an analysis performed goes back to Earth. There is a user-driven analysis which needs to be performed, which supports to identify the direct benefits, cost saving, safety, innovation, and so on. And performing this analysis needs to be done already in the first step at the feasibility studies also. So these are some just long-term steps, just ideas. The first step is a feasibility study. Is it worth to recycle this debris or not? Second is also space-based SSA, RPO, the collection of debris, which is also long-term, and the trade-off scenario. With the trade-off scenario, we validate also the info from the feasibility studies. You do the recycling, and during the trade-off, you decide whether you go forward with returning it to Earth or docking it. And I give now to Jeff the floor.
For the next slide. Hi, my name is Jeffrey Hendriksen. I'm co-founder and chief technical officer of Atmos Space Cargo. We are in space logistics. So looking at the case and looking at all the presentations of today, it's all about, in the end, about logistics as well. It's, as the PhD student Lanie McKinney, if I say correctly, said, so the word logistics come up. It's not only the same then for space debris and dust, but also for lunar, for Mars. You want to get your equipment there, but it's a stepping stone process. You want to also get some of the stuff back. You want to research it. You want to see if your recycling method, your processing method is working. And in the end, where we are working towards to is an infrastructure, which is part of space. So here I have a nice diagram where it's a starting position where us as Atmos or other companies like us provide transport either directly to the place where the materials are, in our case the space debris, for collecting, but not just only for collecting, but can also bring the equipment for collecting or the equipment for processing and so forth. So the first stage is just go, come back, and that's basically our expertise. That's our focus. And more on, as Stella also mentioned, you'll get those intermediate stopping places. A space station, which there's already one there, the ISS. More will come. But you also want to do automated platforms. You don't want to put a lot of money and investment in just crude. You will get those automated platforms for collecting, processing, and so forth. But the materials you may not want to use directly in space. You may want to bring them first back to Earth and recycle them there. The next step, of course, you want to use them in space to build, to get the recycled resources for reuse and trade, or build other structures. It's the same for on the Moon or on the Mars or on any other celestial body. The key element of the logistics to do the first stepping stone is going up and coming back. So that's why I highlighted this slide, is that today, not only Atmos, but several other companies are focusing on these automated platforms for bringing cargo up, but bringing cargo back as a mail service to a space station or as a mail service back from a space station, which is for your equipment being in either processing, recycling, manufacturing, and specifically for the space debris, because it's actually limiting our logistics chains. We need to get rid of it, of utmost importance. And I will give you back to Stella for the conclusions.
Thank you, Jeff. So, in conclusion, on-board low Earth orbit stations can be used for recycling space debris. And we have 3D printers on board. It could be used to print tools. And these capabilities are quite beneficial for future in-space manufacturing, for future cislunar missions also. I do believe that recycling of space debris can generate direct benefits like cost savings, time, safety, contingency, and of course, space debris management, sustainability, and technology innovation. We clearly need in-space logistics or mailing service with the different trade-off scenarios, always assessed by user-driven analysis, because if we don't see any value in the space debris which we want to recycle, it's not worth the investment. Recycling space debris will be the first step for in-space assembly manufacturing and in-situ resource utilization. Thank you.
Thank you very much. Keep the microphone. Thank you very much, Stella and Jeff, for interesting presentation. We have questions.
Hi, Stella. I'm Guillaume Mohara from ArcSpace. Thanks for the presentation. I was wondering, behind all of this work, is there a cost model for modeling the opportunity with different ABC scenarios, and what are the pain points? When does it start making sense? With what technologies and so on?
Well, there is a model, yes, a user-driven framework where costs are considered there. And there are several steps in assessing first the user needs, but also the operation costs, the orbit. There are many, many aspects which need to be. There is the 3 criteria which are applied for the selection of the use cases or the trade-off. One is affordability, actually. The other one is TRL level, of course, and the innovation. So yes, there is, but it hasn't been, that is something which will be performed in the step 1 on the feasibility studies. But there is already a maturation on it. Actually, yes. Actually, thank you, Jeff. With Jeff, we were speaking, we're planning to submit an abstract for the major cost drivers on the 3 scenarios for ESA Cost Engineering Conference, because this is a very important aspect to look at the cost under the different 3 scenarios.
Thank you. I hope those cost analysis can be made, can be distributed afterwards after the conference. We have 2 more questions in the pipe.
Thank you very much for this new and very, very exciting topic that you've described right now. Well, from the slides that you showed us, there are graduation of the size of the space debris. It's very, very small particles like dusts, to very, very large particles. At the point of your talk, you used the term active debris. Have you thought of in terms of talking about very, very small particles, that this debris is extremely biotoxic, or it could be biotoxic? There should be some ways of monitoring or quantifying the biotoxicity of that space debris and avoiding that to be breathed by people or coming in contact with people.
it's a multifaceted question. So there's already known that some of the debris is toxic. I mean, there's even an old case of a defunct satellite which was radioactive and came back. You can Google it. I'm not going to name names there. It's part of why we in the logistics and for Atmos, we are looking into bringing back things in one piece. And it's debris, it's defunct satellites, which you don't want to burn up in the atmosphere. The method of detection, it depends on the sensors which you will have to bring. You have to be selective and be part of the selection and processing of any type of space debris. That's correct. Yeah.
Well, just to add up very, very briefly, as stellar discoveries, we provide sensors that they can be able to quantify the biotoxicity of space debris as well. If you are interested, we can get in touch.
Oh, yes, we are interested because actually on this first step, you can see where we have the feasibility study, value trade-off. In addition, we have space-based SSA, and that's where we were looking at the different sensors, or is it optical, is it LiDAR, you know, different ways to, because before we recycle it, we need to understand what type of, exactly what you said. So I think these are, it's a space-based SSA and debris value also.
So SSA for the non-initiated is space situational awareness. We have one last question.
Sujit from Public Access. I just wanted to get your thoughts on the, I don't know if you're aware, the US Department of Defense, well, Department of War, they recently, the Defense Innovation Unit had put out a project call for getting in proposals from companies to essentially help them deorbit satellites by essentially burning them up. So what are your thoughts on that part of the process? And how does your service work in conjunction with another governmental entity which is trying to do something along a completely different trajectory?
I think that's you. Yes.
Actually, that's a very good question. So recently, the European Space Agency started a working group on the effects of re-entry and the effects of re-entry on the atmosphere. Not only burning up satellites, but also the rocket stages and so forth. I'm very keen to follow this workshop further because I do believe the results will make a change in legislation, not just for Europe, but for the whole world. In the meantime, for, let's say, space debris mitigation, deorbiting and burning up in the atmosphere is the standard. Will this change? Yes. And I think the people from space situation awareness, space traffic control will also see that there things will develop. We won't be able to fly spacecraft just, you know, up and come back. Everything will have a beacon like an airplane, there will be corridors and so forth. It's going to be real space traffic management. Of course, as a company, it's very interesting to apply to just deorbit satellites and burn them up, but it's not our business case. Yeah. I hope that answered some of the question, part of the question.
We can squeeze the last one.
Hi, thanks for the interesting perspective. I'll try to be quick. In terms of logistics, the hypothetical station, would it take care of the decommissioning of the debris itself? Would it rely on deployables or serve as maybe for third-party satellites to take care of the decommissioning and then bring the debris to the station?
It's a two-factor question again.
Yeah, it's a double. So basically, when we were discussing, it's the idea with Jeff, it was like, okay, so we collect, the debris is collected, so let's see, can we dock it to a commercial or to a space station or an unmanned platform to a space station? I think it makes, and then only because you will need, imagine if you have the material to do 3D printing in microgravity and you can print tools which could be beneficial for astronauts' work or activities and so on. That's a game changer if you think about it, but you don't need for them to wait to be launched, to be docked to the ISS, so you can generate some potential cost saving. But then that's also possible with the decommission, and maybe there is material which is completely useless and not beneficial for onboard operations, and then it's decommissioned.
I think I can answer the other part. Also, you have to think it as a space infrastructure and a stepping stone of building up. A lot of companies will play a role in this. So it's not going to be only Atmos. It's going to be a company doing launching up, a company bringing stuff back. There's a company for grinding material, a company for molding material. Everyone here.
Space-based SSA.
Yes,
there's
yeah.
so many different steps for.
Exactly. Yeah, exactly. And it's a stepping stone process. So it will be easier in technology to do unmanned platforms first before you go to manned space station. Yeah, there's the small capsules. You can go to the space station. You can do the larger, like the Dragon, for example. It's kind of a trade-off, but it's a stepping stone.
It's all the cost of flight qualification, I think. So.
Exactly. So I would definitely encourage you to follow us in the next conferences. One is the Clear Space conference in ESA. Yeah, and of course the cost-related conference.
Yeah, exactly. That's it's just an idea which came up, and I personally believe that in-space recycling is the long-term future. We should stop burning and polluting the Earth atmosphere and the stratosphere with burning all this debris. So I think that this is the long-term step. So yeah.
Thank you very much, Stella and Jeff. Thank you for attending this session, which is now closed.